Hello and welcome to the Haskell in-depth section of Fundamentals of Practical Haskell Programming. In this section we will learn about values and expressions, types and type signatures, algebraic data types, type classes, and pattern matching. Welcome to the first video of this section entitled Values and Expressions. In this video we'll look at values of primitive types, functions as values, function application, function composition, anonymous functions, infix functions, sections, and partial application. Before we can build up non-trivial expressions, we'll need to run quickly through Haskell's primitive types. Char is effectively an enumeration representing Unicode characters. Integer is an arbitrary precision integer intended to model a real mathematical integer. Int is a machine integer, typically a 64-bit signed value on 64-bit platforms. And float and double. These are single and double precision floating point numbers representing reals. Almost everything else is defined in terms of these primitive types, even other numeric types such as ratio and complex, and the standard string type. These types have literal syntax for defining instances, as do string and other string types with various language extensions. And we'll talk more about composite types and algebraic data types later. But now we have enough information to look at expressions in more detail. So let's play around with expressions in GHCI. So start GHCI, stack GHCI. First we'll look at the differences between int and integer. We'll declare A has type int. This is a type signature and we'll talk more about these later. Suffice it to say now that this is how we fix A to be a specific concrete type. Semicolon, A equals 1, 2, 3, 4. And we use sprint to look at its current state. Sprint tells us that it's underscore, which is an unforced thunk. A has not yet been evaluated. Type A tells us its type, which is int. Then we can type its name, A, to evaluate it. 1, 2, 3, 4. And again, we can go back and use sprint on it again. And it tells us now that the value has been forced. It's no longer an underscore. And now we're going to create B with type integer and assign it to the value 2 to the power of 70, which is clearly bigger than 64 bits. Sprint on B tells us it's unforced. Type B tells us it's an integer. B evaluates it. Sprint B tells us it's now been forced. Note that if we attempt to assign such a large number to an int, it will instead be assigned 0. As noted in previous videos, Haskell does not allow implicit conversions between numeric types by design, and we'll look more into num and the related type classes later. Functions are where it's at. Now we're going to drill down deeper into functions, syntax, application, and composition. We've seen a few functions already, but let's talk a bit more about how we declare them. Firstly, we're going to import the data.list module. This gives us access to the intercalate function. We'll look at its type. This is a general purpose function which takes a list of lists, another list of the same type, and yields another list. And this can be used to join a list of strings using a separator, although it's much more general than this. For example, we'll apply intercalate to the string colon, which is the path separator on Unix platforms, and to a list of strings representing Unix paths. Lo and behold, the result is a string which is the concatenation of the input strings with a separator, in this case the colon here. Now let's write a format list function that uses intercalate to pretty print a list of strings. Format list, it's going to take 4 arguments, s, e, sep, and x's. We'll type out the definition of the function. As we can see, the function's name and arguments are listed separated by a white space immediately before the equals sign. Format list is the name, S, E, sep, x's are the argument names. S is the start delimiter, E is the end delimiter, sep is the argument separator, x's is a list of arguments. And we can try that function out. Format list applied to a string containing an open parens, a string containing a closed parens, a string containing a comma and a space, and a list of values. We can see that this function applies show to each of the x's, so it converts these numbers 1, 2, 3, 4 into strings, yielding a list of strings here, which we then pass along with the separator to intercalate. And then we add S and E to the beginning and the end respectively. For all practical purposes, this can be considered to be a function in 4 arguments, though in fact all functions in Haskell are really functions in a single argument, which we'll talk a little bit about later. Conceptually, this function application involves the function application operator, which is the white space, and thus Haskell adopts the tersest possible syntax for function application. This makes sense since this is one of the most common things we will do in our Haskell programs. Function application also has the highest precedence of any operator. This design choice was made to minimize the number of parentheses required. Let's consider the function square takes an argument x and evaluates to x to the power of 2. And another function, square sum, taking 2 arguments, x and y, and it evaluates to square of x plus square of y. And we can apply square sum to 3 and 4 to yield 25. Because of the definition of white space as a function application operator, we do not need to parenthesize the arguments. Furthermore, we do not need to parenthesize the function applications since they are evaluated before the plus operator. There is a second function application operator, and this is the $sign. It has the lowest precedence, and it can be used to reduce the parentheses required in certain situations. For example, f equals let s equals hello world in put strlen dollar open parens plus plus s plus plus close parens. Here we introduce a let binding, a name s assigned to the value hello world. And we introduce it into this expression. We take s and we add open parens before it and close parens after it, and then pass the result to put strlen. And we can evaluate f by typing its name and getting the expected result. An alternative way of expressing this without dollar will be as follows. F equals let s equals hello world in put strlen parens open parens plus plus s plus plus close parens. They yield exactly the same value. However, dollar also allows us to treat function application just like a function, and it can be passed around to other functions. Now let's talk about function composition. Function composition is the act of pipelining the result of one function into the input of another. This creates a third composite function. Let's make a function that doubles its argument. Double it. It takes x and it evaluates to x times 2. And its type a to a, where a has the constraint num. We'll try it out. Double it 5. Yields a value 10. Let's make another function that adds 10 to its argument. Add 10, x equals x plus 10. The type of add 10 is also a maps to a, where a is constrained by num a. You can apply add 10 to 15. Yields the result 25. Let's use these two functions together the obvious way. So we do add 10 applied to the result of double it applied to 5. So double it 5 will yield 10, and then we'll add 10 to it to give the result 20. The process of applying functions to the results of other functions is so common that Haskell has an operator specifically for it. This is the dot composition operator, and we can use it to get an equivalent transformation. So open parens add 10 dot double it, close parens, applied to 5, yields the value 20. And this is read, add 10 composed with double it, applied to 5. And you may be asking yourself what the point of this is. So we'll extend it to more functions to demonstrate that. Let's take the result of this composition and then convert it to a string using the show function. This could be done as follows. Show applied to add 10 applied to double it applied to 5 with 2 sets of parens yields the string 20. Using composition, we can instead do show composed with add 10 composed with double it and apply that all to 5 to yield the same result. And this generalizes to an arbitrary number of functions as long as the result types and input types chain properly. Composition of functions in this way emphasizes the valueness of the composition. For example, we can say f equals show composed with add 10 composed with double it. And we can look at its type, and it takes some type A and evaluates to a string, where A satisfies the constraints that it must have an instance for show and num. As with any other function, this composite function can be passed around to higher order functions. So we can map f over a list. So f is applied element-wise to the list 10, 11, 12, 13, 14 to yield the string representation of those values doubled with 10 added to them. And of course, due to referential transparency, this is exactly equivalent to passing the 3 functions composed together. For example, map show dot add 10 dot double it applied to the same list. Notice how in this last expression the function passed to map has no name. And passing anonymous functions around is a very powerful concept. Functions are so important in Haskell that we get to refer them by name or by no name at all. And another way to construct a function without a name is using Haskell's Lambda syntax. Let's consider a trivial example. Lambda x maps to x plus 1. Here Haskell uses the backslash, which is pronounced lambda, to represent the Greek lambda character. And this is the function that takes an operand, x, and adds 1 to it. Lambdas, just like every other function in Haskell, always take exactly 1 argument. However, Haskell provides syntactic sugar that allows us to define functions with more than 1 argument, which are then desugared to single-valued functions. For example, we'll comment that out with a double dash to write another expression. This expression is going to be lambda x y, 2 arguments, maps to x plus y, a summing function. The Haskell compiler can desugar this to a function in 1 argument. For example, lambda x maps to lambda y maps to x plus y. Alternatively, with some parentheses, this corresponds to lambda x maps to parens lambda y maps to x plus y, close parens. The right arrow map to operator is right associative, so the parentheses in the last example are not required, though sometimes they're helpful. Note that much like functions in general, the names of the arguments, in this case x and y, do not matter as long as they do not collide with any of the free variables in the expression. So how is this useful? Well, let's define a function with a scoped helper function. And we're going to create a multi-line expression in GHCI. And we're going to use the colon brace and colon close brace syntax for that. So, colon brace to start a multi-line statement or declaration. And we're going to create a function called parenthesize words. It's going to take an argument s. This is going to be the result of applying unwords to, with dollar, map, parenthesize word, words, s. And in the context of that expression, using a where binding, we will define parenthesized word as follows. It takes an s, it's a different s because it's in a child scope. It evaluates to the string open parens concatenated with s, concatenated with the string close parens. Now we'll end the multi-line editing session with colon close brace, and we can apply our function parenthesized words to we love Haskell. There we go. Each individual word of the string is parenthesized. Words is a standard function in the prelude which takes a string and splits it on the white space to yield a list of strings, list of words in this case. Unwords is the complementary function which takes a list of strings and yields a string, which is the concatenation of each of the strings with white space. And then we map our parenthesized word helper function over each of those words. Now it's important to note that parenthesized word is only accessible in the scope of parenthesized words plural because of the where binding. Now, for better or worse, we might consider having to invent a name for the helper function to be an inconvenience. And certainly we only use the function once, so let's use a lambda expression instead. That would be parenthesize words s equals unwords $map. We'll start a lambda here. Lambda s maps to string open parens plus plus s plus plus string close parens applied to words s. And we can confirm that it yields the same result. We love Haskell. Lambdas also provide another perspective on the valueness of functions, since that's being passed as a value to map. Given referential transparency, it should be clear that parenthesized word, this function here, is exactly equivalent to this expression here. And in fact, there are many different ways of defining the parenthesized word helper. Here are a few examples. Parenthesize word, just assigning the lambda directly, since they are referentially transparent and equivalent. You can apply that to a string. It parenthesizes it. We can declare it in the sort of traditional function way as follows. Parenthesized word s equals open parens plus plus s plus plus close parens. Apply it to the word love. And here's a third option. Again, no arguments, so emphasizing the valueness of the expression. Equals parens string open parens plus plus close parens dot, which is composed with open parens plus plus the close paren string close paren. And we can apply that to the word functions. This last representation uses function composition from before, along with a bit of new syntax. For example, this sub-expression. Let's look at its type. This takes a list of char and maps to a list of char. Similarly, the second expression takes a list of char and yields a list of char. This first function is the function which prepends an open parens onto its operand. Similarly, this function is the function that appends close parens to its operand. And these are both known as sections. Sections are a specific type of partial function application, since we are providing fewer than the full set of arguments to a function. In both cases, the function is plus plus, which is a binary function, normally takes 2 arguments. Let's define another named function and use it as an infix function. The function is going to be func x y. It's defined as show x concatenated with show y. And its type is from a to a1, so 2 different type variables, to list of char, which is string. And both a and a1, which can be different types, are constrained by show. We can also declare this function infix style by surrounding its name with backticks. X backtick func backtick y equals show x plus plus show y. This has the same type. And the functions are exactly equivalent. And this function can be used prefix or infix regardless of how it's declared. So func AAA BBB concatenates the show of both strings together. AAA backtick func backtick applied to BBB. Exactly the same result. And this is true of any function. We can also define left and right sections. So left section is a function is equal to 5 backtick func backtick. We'll try that again. We need parentheses. left section equals parens 5 backtick func backtick. When you look at its type, it takes A1 and yields a string. We can apply it to a string. We get 5, 6. Similarly, right section equals parens backtick func backtick 5 as a string. And we apply this to a value. We get 6 and 5, as you'd expect. So a left section is a function with its left operand specified, and a right section is the same binary function but with its right operand specified. The result in both cases is a function in the remaining operand. And sections are a specific example of the much more general concept of partial function application. So, given an n-argument function, we can supply all n arguments. So let's declare foo x, y, z, which is the concatenation of x, y, and z. And we can apply it to 3 strings like that, getting the expected result. In this situation, the function is said to be saturated. We've supplied all n arguments. Partial applications where we supply fewer than n arguments. In general, a function in n arguments applied to a single argument will yield a function in n-1 arguments. So we can look at the type of foo, which is list of A to list of A to list of A to list of A. We'll apply it to a single argument. X equals foo applied to AAA. And we can look at the type of X. We can see that it's list of char to list of char to list of char, which is n-1 arguments. You'll observe also that A is taken on the concrete type of char since we applied it to a list of char. Let's apply X to another argument. Y equals X applied to BBB. The type of Y is list of char to char, 1 argument less than before. Finally, we'll apply Y to CCC. The type of Z is list of char, or string. And we can look at the value of Z now, since it's a concrete value, and it's a concatenation of the 3 strings. At each stage, each partially applied function is a regular function, and they have values that can be passed around. We can also assign names to them, as we saw, and this is incredibly powerful, and you'll see it everywhere in Haskell. We'll have a few more examples. So let's introduce the notation for a range in Haskell. So this defines a list that is a range starting at 1 and going up to the value 10. Press enter to evaluate it. Let's consider filtering this list to retain all the elements less than 5. To do that, we can declare a function less than 5 in one argument x, and it evaluates to x less than 5. It's a Boolean expression. It will return true if x is less than 5, false otherwise. We can use the filter higher order function to apply less than 5 to the elements of that range. And lo and behold, we get 1, 2, 3, 4, which are the 4 elements whose values are less than 5 from that list. We could also replace this less than 5 function with a lambda in order to avoid having to invent a name for it, which might make sense since we only use it once. Filter lambda x maps to x less than 5, apply to 1.10, achieving exactly the same result. However, less than is a binary function, and so we can partially apply it to 5 on the right hand side to get the right section. So this can be reduced to filter less than 5 applied to 1.10, yielding exactly the same result. And we can go even further by filtering and then doubling each element. So to double each element, we want to apply the *2 function. So we map *2 to each element from the filter. So use $, function application, filter, less than 5, applied to 1.10, yielding 2, 4, 6, 8. So now we've looked at values, expressions, and functions in many different guises.